summer semester. So Marissa, if you'd go ahead and hit record.
Done.
And I think I'll go ahead and turn it over to Brian DuSell from Notre Dame University, or University of Notre Dame. And Brian's going to give us a talk on how to install literally anything with a practical guide to Singularity. I think Singularity is a technology that we've all been very familiar with in discussions, but I'd like to see some hands-on applications and really start diving into this thing. So without further ado, Brian, take it away.
All right, thank you very much. So as he said, my name is Brian DuSell. I'm from the University of Notre Dame. You can find me on GitHub and Twitter. This tutorial is actually available on GitHub, on my GitHub account, under bdusell/singularity-tutorial. So if you want to look at the code later on, then you are free to do so. So I'll introduce who I am a little bit. So I'm actually just a grad student. I should point out that I am not affiliated with Singularity in any official capacity. I actually am a computer science student studying natural language processing with Dr. David Chang. So what I want to accomplish with this talk is to basically segue from the previous tech talks that we've had on this mailing list and transition from things like Spec and Docker to Singularity. So I think in the previous tech talk, we had a pretty great introduction to what containers are. Docker is more oriented towards things like cloud computing, so building web apps and things like that. Whereas Singularity is designed more with scientific computing in mind. So in this presentation, I'd like to cover the sort of basic Singularity workflow. So searching for base images, defining new images, and running your own containers. And to do this, I'll be walking through a real example of running a GPU-accelerated program in Python based on PITorch within Singularity. And finally, at the end, I'll impart some closing thoughts on maybe setting up a new standard for research quality code. So trying to release your code along with the container image that you developed your code in so that you can ensure that it will run on anywhere that has Singularity installed. Okay, so what is Singularity? Well, as you may know, like Docker, Singularity is a containerization system. It is a program that allows you to run processes inside of containers. And as I mentioned, it is designed for scientific computing specifically, rather than things like web apps. It's a lot more convenient to configure for shared computing environments like you have on HPC clusters. And the great thing about Singularity and containers in general is that it allows you to package an execution environment together with your code. So the environment that your code assumes exists on the machine is actually part of your project now. And this maximizes the reproducibility of your code on other machines. The other great thing about it, and this has to do with the sort of tongue-in-cheek title of my talk, is that it allows you to install essentially arbitrary software in a non-root user account with pretty minimal effort. Okay, so to get started, some of you may already be familiar with Docker. If you're not, that's okay. I'll explain everything in detail eventually. But just in case you've seen the Docker definition language before, here is a pretty simple image definition on the left, and on the right is the equivalent Singularity definition. And as you'll see, they are almost identical. The repeated part is essentially just a list of shell commands, and the only thing that's different is basically the boilerplate code. So why do we like Singularity, and why would we use it over Docker? Well, for one, it uses, I think, a much simpler paradigm than Docker does. The nice thing in Singularity is that container images are just flat files. So if you use Docker, then you may know that Dockers are all managed by a central Docker daemon that runs on your host. And if you want to transfer Docker images, generally you use the Docker command to push or pull images to or from Docker repositories. But in the Singularity world, images are just .zip files. They're just plain old files. So any tool that works with regular old files, you can use with Singularity images. So this lets you use things like SCP to transfer an image, say, from your laptop to your HPC cluster. Another thing about Singularity is that it generally views containers as one-and-done processes. So a process that you run once, you get some results, and then the container is destroyed. Whereas in Docker, it's more oriented towards running containers as potentially long-running services like web servers. But in Singularity, we're generally using them for scientific applications where we run some compute-intensive process, it writes out some results, and we're done. So this makes sense. We're not building web servers. In Singularity, there is no more Docker daemon or Docker registries. Like I said, images are just files. But a very important feature and a deliberate design decision in Singularity is the fact that it is fully compatible with Docker images. So Docker, of course, has exploded in popularity over recent years. And right now there is a plethora of very high-quality images available for just about any major software library that you can imagine. So the fact that Singularity is compatible with Docker images means that you can leverage this existing very rich ecosystem of images. And something that's very near and dear to my heart is the fact that Singularity supports NVIDIA GPUs right out of the box. So you don't have to worry about mapping drivers into your container. Singularity just does it for you. It's just you just add --NV to your command, and it just works. So it's awesome. All right. So I like to think of Singularity and containers more broadly as addressing a couple of problems in the context of scientific computing. So the first problem is what I would call the portability problem, or you could say it has to do with reproducibility. And this has to do with the fact that writing code that is truly portable, that can run on more or less any system, takes a lot of hard work. So when you're restricting yourself to pretty simple, basic functions in one programming language, this is not too tough. But as soon as you're making things like external calls to executables, then this gets a little more hairy. On the flip side, there are many times when you want to run somebody else's code. And if you are unfamiliar with the framework that they use, you may not be aware of all the software dependencies that you need to install on your system. So if someone just gives you a container, then you don't need to worry about that at all. You can just run their code in the container and all the dependencies should be met. The second problem is what I call the installation problem, and that, again, this has to do with the title of my talk. And this has to do with the rather mundane fact that installing software on an HPC cluster as a non-root user is generally pretty difficult and very time-consuming. I've spent, I think, literal days installing a custom version of Python just to get TK to work. All right, so let's look at the portability problem. So all code that you write makes some sort of assumption about the execution environment. And this may or may not be explicitly documented. And especially when you're dealing with research quality code, it's often not. So you'll often deal with code that runs just fine on one machine, but when you try to port it to another one, then it fails with cryptic errors. And here's a little motivating example. So this is some plain old Python code, but not all Python syntax works in all Python versions. So this is an example of set comprehension syntax, and it only works in Python 3 and above. If you use a function like subprocess.run, this only works in Python 3.5 and above. And if you're making an external call to an executable, then you better make sure that that's available on the system that you're running on. Okay, and back to the installation problem. So HPC clusters in general give you a Linux account that does not have root access. It's a shared file system. That's the case here at Notre Dame, at least. So you can't use built-in package managers like Yum or apt to install packages. Instead, you usually need to rely on the staff to install packages for you. And although it is almost always possible to build a library yourself without root privileges, it can be a very time-consuming process, especially when you need to recompile things that they depend on. So you need to dig through documentation, figure out how to compile things with non-standard locations. It can be a very frustrating process. Another point is that you may sometimes want to install an older version of a library on purpose. I've had to do this before. I once used Singularity to install a very old version of TensorFlow so I could run someone else's code. And there's also the phenomenon of software rot. So your HPC cluster may frequently update the software that they provide, and this might break code that worked a month ago, and now all of a sudden it doesn't work anymore. I have an anecdote about this. I used to use a deep learning library called DyNet, and I don't mean to pick on DyNet specifically, but this is just a salient example. DyNet used to require a certain version of GCC to compile it. This was an older version of GCC, and a while back, our HPC cluster at Notre Dame removed that old version of GCC. So if I wanted to update DyNet after that point, then I would need to install my own version of GCC, compile it from source, and then figure out how to get DyNet to compile itself with a compiler in a non-standard location. So at that point, I switched to PITorch. So the solution to all this, of course, is containers. So I know in the previous talk, we got a very nice description of what a container is, but I'll review it very quickly. So containers are what I would call a massively popular software isolation technique, particularly thanks to Docker, but Docker is not the only containerization software out there. You can think of a container as being an operating system within an operating system, like a VM, but unlike a VM, it does not virtualize the processor. So you don't have the overhead of running a hypervisor. You don't have overhead for translating machine instructions. Instead, the kernel of the host OS is shared with the containerized process. Essentially, it treats the containerized process as a brain in a jar. So it spoofs the file system and the network it has access to, so it thinks it's its own independent, clean little system. And let's review some terminology just to make sure we're all on the same page. So a container, you could say, is just a process that is running within a containerized environment. And containerized, in this case, refers to an isolated environment, something that is distinct from the host system and doesn't have full access to it. An image, on the other hand, is something that you can instantiate containers from. So an image, I would say, is a snapshot of an execution environment from which a container can be instantiated. So a class is to an object as an image is to a container, you might say. And finally, an image definition is simply some sort of deterministic set of instructions for building an image. So usually these are just a set of shell commands in a text file. So this is like your Docker file in Docker or your definition file in Singularity. All right, so how does Singularity solve these problems? Well, in terms of portability, because your image contains all of the program's dependencies, except for the OS kernel, you can run it anywhere that Singularity is installed. And I put a little asterisk there because there are some ways in which the environment of the host OS might unexpectedly leak into the container. I think this is a deliberate design decision on Singularity's part. So for example, unlike in Docker, in Singularity, environment variables are inherited into the containerized process from the host. So that's something you should be aware of. But in terms of software dependencies, everything is included in the image. In terms of installation, because the root file system of the image is totally distinct from that of the host, you can freely install software into the image as if you were the root user without affecting the host. And you need to actually run as root when you're building the image. This has to do with the fact that user permissions are actually implemented in the kernel. So if you want to pretend to be root, you actually need to be root on the host when you do it. But you can do that, say, on a private workstation where you do have root access, and then transfer the image to an HPC cluster, and then run that image as a user without root privileges. Okay, so here is Singularity in a single slide. So these are the basic Singularity commands. And believe it or not, this small set of commands essentially covers the entirety of this tutorial, which really speaks to the simplicity of Singularity. So the first command is simply building an image. We need to run as root, so we have sudo. There is also an option to run Singularity Build as a non-root user by sending the definition to a public build server. I personally have had trouble getting this to work with very large images, but that's an option to consider. So there is potentially a way to run this from your HPC cluster directly without needing to run it and install Singularity on your own private workstation. But that's Singularity Build. You're simply converting a definition file into an image file, which has the extension .sif. So in Singularity, .sif is an image file. You can also download an image using Singularity Pull. There are several sources from which you can pull images. One is the official Singularity Library. That's the example that is shown here. You can also pull any Docker image, so you can give an address to a Docker image. You can pull from the official Docker hub. There's really nothing to it. It just saves it to a flat .zip file. The third command is running a command. That would be Singularity exec. So you call Singularity exec on a .zip file, and then you run a command that you want to run inside the containerized process. Adding GPU support is very easy. You just add --nv to the exec command. It's really that simple. It's beautiful. So as long as you have the NVIDIA drivers set up properly on the host, then this will happily map the drivers into the container. And finally, you can open an interactive shell, like a bash shell, inside your container just by running Singularity shell. Okay, so when you're dealing with Singularity, the general workflow looks like this. So you start by defining your image in a .def file. The extension actually doesn't matter. And the first step in doing that is to choose an appropriate base image. Usually this is some sort of Linux distribution, or it could be an image with a particular library pre-installed, like TensorFlow or PyTorch, something like that. Then you take that definition file and use it to build a .sif file. This requires root access, as I mentioned. And then on your HPC cluster, or wherever you want to run the containerized process, you instantiate the image as a container using Singularity exec. And this step, crucially, does not require root. And if you run into errors with dependencies not being met, then you tweak your image definition a little bit, and you will know that you're done when your program stops crashing. Okay, so at this point, I'll be getting into the more demo-y section of this talk. If you want to follow along, and I won't be having you run commands in real time, so you don't actually need to have Singularity installed. But if you want to take a closer look at the code while I'm talking, then you can visit this address. It's just my GitHub account, and the repository is called Singularity-tutorial. Okay, so we will be starting with a relatively simple PyTorch program. And this program will do a couple of interesting things. So the basic program trains a neural network to learn the XOR function. After it does that, it makes a plot using matplotlib, so it should open up a window using TK. And finally, it saves the trained neural network to an output file. So let's open up the code on GitHub. Hopefully you can all see this all right. But this is what the Python code looks like. You don't need to know the details, but here it is. We're using PyTorch. This will be running on the CPU. We're not getting to the GPU just yet. but it trains the model, it will save it to an output file, and finally it will show a plot. Okay, so now we want to wrap this up inside of a Singularity environment. So we're going to start by defining our definition file. The very first step is always to pick a base image. And your go-to sources will be either Docker Hub or Singularity Library. There's another site called Singularity Hub. And I would say 99% of the time you'll be using an image from here, but you can pick many different sources for images. In general, if you want to find an image for library X, just type in X Docker into your search bar. It's really that simple. The Docker ecosystem is very active, so you can find an image for just about anything. All right, so let's see what our definition file will look like. All right, so this is the definition file that we will use for this first program. So the first part of the file is this boilerplate code. So this is called the header section. It's just you have some keywords followed by colons. The only one that's required for all definition files is this bootstrap header. And bootstrap just defines what mode you're using to download or locate the base image. So library pulls an image from the official Singularity library. And in this case, we are selecting the Ubuntu 18.04 base image. So our image will be based on Ubuntu, and we will be running some additional commands inside a container to take the image to a desired final state. And then it is from that final state, after we have installed some libraries of our own, that we will instantiate our own containers. So every Singularity definition file has a number of sections. The most important one, the one that you'll use in, I hope, every container, would be this %post section. Every section begins with some % and a keyword. So in the case of Ubuntu, we will be, in our definition, we will be installing Python, and we will be installing all of the Python libraries that we need. In our case, we want to install Torch, NumPy, and Matplotlib. So they're required for training the neural network and for showing the plot at the end. So in Ubuntu, you would do this as follows. First, we call apt-get update-y. This is very important. It basically updates the package list so we know where to find the latest packages. And this is just a kind of a standard incantation for building images based off of Ubuntu. You can also use a very lightweight Linux distribution like Alpine. I won't be getting to that in this tutorial, mostly because the final GPU-supported image that I'll use does not use Alpine, but that's something that's worth looking at as well. So you'll notice that the post section is essentially just a list of shell commands. And if you're used to Docker, you might be used to including a little ampersand backslash at the end of every line. This is because, I don't want to get into the weeds too much, but this is because Docker has this concept of image layers, and you want to conserve the number of layers that you use. In Singularity, this doesn't matter. Everything's just one file in the end anyway. And there is essentially an implicit and at the end of every line. So the Singularity Build command will stop at the first error that occurs. So if any of these commands exits with a non-zero exit code, then the build will stop itself. It won't continue in an undefined state. All right, so I covered apt-get update. The next command is our apt-get install command. This extra stuff here is just to make sure that it doesn't try to run any interactive prompts, which would cause it to hang indefinitely. And we're just installing some app packages, Python 3, Python TK, things that we need to get plotting to work. And we're also installing pip, which is like the package manager for Python. This is to reduce the image format somewhat. This is basically undoing what we did in apt-get update. It's just removing some unnecessary data. And finally, the last line in our definition is where we use pip to install the Python modules themselves. Okay, so that was a walkthrough of our image definition. Not too complicated, I think. The next step is to build the image. And here I have a pre-recorded session. I'm not going to play the entire thing. It does tend to take a while. So here we're using sudo Singularity Build. And if anyone has any questions at this point, this would be a good time to jump in.
Hi, this is Tyler. Can you hear me okay?
Yeah, I can hear you.
So my question is, and maybe you answered this and I missed it, but does Singularity do anything to reduce the overhead of spinning up an image? For example, if the installation steps are heavy, do you need to do it every time you're spinning up a process? Or does Singularity like cache the build file in some way?
That's a good question. So when you're actually running a container, the image is already precompiled, you might say. So we're building the image, but we only need to build the image once. Every time we want to run a container based off that image, we don't need to rerun the build process itself. As for optimizing the startup process, I'm not aware of the technical details of how Singularity starts up processes. I don't know if it does anything special that Docker does not. But yeah, did that answer your question?
I think so, yes, and I think that is, okay, that makes sense. Thank you.
All right, so I'm going to try to skip ahead a little bit here. It's not important to watch the entire thing, but that's a taste of what the build process looks like when you're using Ubuntu. You'll get some different output if you're using something like Alpine. Hopefully we'll get to see the end of it. It will unfreeze itself eventually. There we go. At this point, it's installing Python modules, creating the CIF file. And that is it. So we created this file, version1.sif. Okay, so if we were to run this image, here's what it would look like. So I have another recording here. So we have our version1.sif file that we created. And you'll notice after version1.sif, here I'll go back so we can see the full command. Here we go. Okay. You'll see we have Singularity exec, the name of our image, and then after the image name, we run the command that we want to run inside of the container. So in our case, we're running the Python 3 command, and then the name of the file, the name of the Python program that we want to run. And I wrote my script so that you can provide the name of an output file. So we're saving our file. We're saving our model in a file called model.pt in the current working directory. So this is what running the program looks like. So it has this output that reports the progress of the training process. It saves the model to a file. And if I were running this for real, then at the end, we would have this plot show up. We would have something like this show up. Okay. And you'll notice I didn't get to show you running this for real, but you would notice that after the program ran, the file output.pt exists in the current working directory on the host. And this is a key difference between Singularity and Docker. So if you're from the Docker world, you may know that by default, the container does not have any direct access to the file system on the host unless you explicitly give it permission. So this is called bind mounting. Docker also has another concept called volumes. We're not going to get into that. But Singularity, for the sake of convenience, essentially bind mounts a few directories by default. And these include your home directory, the current working directory, and some other system-wide directories that apparently have changed from version to version of Singularity. But the important things you need to memorize are the home directory and current working directory. So this is actually pretty important to remember when you're using Singularity because, for example, on my HPC cluster, I often store my log files on a device that is outside of my home directory and current working directory. So when I first started using Singularity, I was getting weird errors saying that the log directory did not exist. And this is because I did not tell Singularity that it had access to that directory. So if you want to do something like that, you need to use the -- bind flag with the exec command to give it access to any directories that are outside of the home or current working directory. And it's important to note that any files that are, say, written to bound directories will still exist after the container is shut down. Okay, and the other thing, I mentioned this a little bit before, environment variables are inherited. This is a big difference from Docker. You can disable this functionality with -- clean env. But yes, the important thing to remember is Singularity inherits environment variables from the host by default. I should also point out that in the definition file, there are many different types of section that I did not describe because it's not essential to get into them in the scope of this talk. But another additional block you can include is the environment block. And this will define environment variables that get defined every time you start a container from an image. I will show an example of this later on. All right, that example is right now, in fact. So let's look at a much more computationally intensive PyTorch program. So I will be showing you a program. This comes from the official PyTorch repository. It trains a neural network on a section of Wikipedia text. And this program essentially requires GPU acceleration, otherwise it will run very slowly. So we require CUDA. And here is what the actual structure of the code doesn't matter too much. The main code is, I believe, here. If you're following along with the repository, then you can feel free to look at the details. Okay, so again, we have the code, but we don't have a Singularity image yet. So let's start building a Singularity environment around this code. So we know that this code will depend on CUDA because we want to run it on GPU. So let's look at how I decided which space image to use. So let's visit the web page for the official CUDA Docker images. So this website is Docker Hub, and this is the page for CUDA. And in their case, they have this nice little README on the front page that explains what all the different tags mean. Let me zoom in a little bit here. And here's a list of possible images we could pick. All of these different tags mean something. Let's go with the latest CUDA image. So in this case, 10.1. And you'll notice that some of these tags are appended with Ubuntu 18.04. That's just the name of the operating system or the Linux distro that's based on. Some of them have devel in the name, which means that they include the CUDA header files, which are necessary if you need to, say, compile something against CUDA. And some of them have this cuDNN. cuDNN is just a library which contains some highly optimized neural network operations. So this is something that PyTorch can use, so we definitely do want to include that. So for various reasons, I ended up choosing this image here. So 10.1, cuDNN 7, devel, Ubuntu 18.04. Devel is required because we are building PyTorch when we install it, and cuDNN because we're using neural networks. Okay, so the beautiful thing about GPU support and Singularity is that legitimately the only change we'll be making to our definition file is just switching that base image. All right, so the most important step was just picking that base image, but after that, because it's also using Ubuntu, the only thing we need to change is this from line. We also need to change the bootstrap here. So I mentioned before, bootstrap is the only required header, and it determines what the address of the image means. It tells the Singularity where to find the image. In this case, we're switched because we're pulling an image from Docker Hub. We say bootstrap Docker and then the name of the image, and everything else is the same. So this is the same code, and this will add GPU support to our program. So I think that's pretty awesome. Usually that's a lot more difficult to set up. I won't go through running it. The output of the program isn't too important for the sake of the tutorial. It would look something like this. Again, this is just an example I took from the official PyTorch example repository. Okay, and truth be told, that is pretty much the end of the basic Singularity tutorial. From this point forward, I'll be giving some more workflow-oriented tips, and these will actually be specific to Python, but you can take these concepts and apply them to other programming languages that you use. So this next section will be about how to separate Python modules from your image. So in the examples I just showed you, we started with a base Ubuntu image, and we just installed everything we needed into the image itself. So we crammed all of, we crammed Python and all of our Python modules into the image. And the image actually does not need to be that big. So I'm going to talk about how you can separate the stuff that doesn't need to be in the image from the image. Okay, so yeah, a problem with the approach I just showed you is that whenever you want to install a new Python module, which may be quite frequent, you need to rebuild the entire image, which can take a while because you need to start from scratch every time. One of the downsides of Singularity compared to Docker is that Singularity does not have cacheable image layers. If you want to rebuild an image, you need to run the entire install process over again. So if we can avoid rebuilding the image, that would be nice. So one candidate for separating things out of the image is the Python modules. So it's actually pretty easy to install a Python module without root access. And we can do this using a package manager for Python. Pip is not quite what I have in mind. We'll be using something called Pippin. You may be familiar with certain frameworks, like say Node.js or Ruby, which have this concept of package files and lock files. So, for example, if you've worked with Node.js, then you may have dealt with package.json, which lists all the JavaScript packages that your code depends on. So we'll be using the equivalent thing for Python. So how this works is that the package manager will take the Python packages that we specify, and it will install them in the current working directory on the host. So it will not install them inside the container. the container will have access to them because they're in the current working directory, but the packages will be stored on the host, and they will persist outside of the scope of the container. So you can repeatedly run the container without needing to reinstall the packages every time. And the container will be essentially just for running the packages, right? So the packages are just data. They're just files that exist on the host system. But when we spin up the container, it's the thing that can actually run them with the proper versions and everything, with the proper versions of Python. Okay, so we want to get to a place where we only rely on the image for just the basic Ubuntu, CUDA, and Python environment. In other words, things that are easiest to install when we have root access. So this will make our image smaller and more reusable across different projects. Okay, so Pippin. Pippin is a package manager for Python. So you can install modules into the current working directory using pipenv install and the name of the module. So for example, you'd have pipenv install torch. It's based on virtual env, which is like, it lets you install a very lightweight, isolated version of Python. It's not a container, but it's like a really cheap method of sort of faking a fresh Python installation that doesn't have any third-party packages installed. And it can do this in a user directory. That's the nice thing. So this will store packages in a local directory named .venv. And pipenv will also install, it will also record all the packages that you install in files called pipfile and pipfile.lock. So this will ensure that your repository remembers the exact versions of the packages that you use. The pipfile.lock is where those exact versions are recorded. But this is nice because you can commit pipfile and pipfile.lock to your Git repository, but you don't need to put the third-party code into your repository. Instead, since you have the exact versions recorded, you can save just the lock file, and then when someone else needs to install those packages, they just run pipenv install, and it automatically installs the exact same versions. And you can do this without including the Python packages in your Singularity image. So it's important to note that if you use this technique, then when you spin up your let's say you're trying to run your program on another host. So that host is Singularity installed, and you can spin up new containers from that image, but of course you won't have the .venv directory created yet. So you need to initialize that once by running pipenv install inside the Singularity container. And that will download and install the Python packages. And then afterwards, when you want to run Python programs with access to those Python packages, you run a command that looks like this. So Singularity exec, the name of your image, and instead of running just a plain Python command, you now run pipenv run Python and then the name of your program. Right, so we have another layer of abstraction here. So we have Python running inside of pipenv, running inside of Singularity, and it's turtles all the way down. And I want to look real quick at what the image definition looks like for that method. And that would look like this. Okay, so this is what I would call the final and best version of our Singularity definition file. So as before, we're running the same GPU program that we did in the last example. We're basing our image off the same CUDA Ubuntu image. We're running a lot of the same apt commands, except this time I had to install Python 3 dev for some reason. I think that had to do with pipenv. But we've gotten rid of a couple things. Let's see. Yeah, the details are not super important, but this, if you want to use this method, then just base your project off of this definition file. At the end, we're just installing pipenv, and crucially, we are not installing torch, numpy, or matplotlib at this point. We're just installing pipenv, and pipenv is now the tool that will manage our Python dependencies. And finally, I did say we would include an example of the environment block. All these environment variables are things that are required to make pipenv work. These are just mundane details. You need to set a certain encoding. This one is very important. By default, pipenv actually does not store things in the current working directory, which means it basically would not play nice with containers at all. This environment variable fixes that. And after that, the program should run like before. Looking at the time, I think I can just skip what running that looks like. If you're interested, you can. You're free to look at the repository. Otherwise, it should look exactly the same as the previous example.
Hey, Brian, I'd allow probably 5 to 10 minutes or something like that for questions. We've had quite a stream going in the chat box. It looks like you're either covering most of the questions or the community behind the scenes are chatting and discussing them, but there's probably still a few outsiders.
Okay, yeah, that's great. I think we're good on time. I think I have just a couple more slides.
Oh yeah, that sounds good.
Okay, so I'll try to wrap this up soon. So these are just my parting comments on some best practices with Singularity. Okay, so let's think about how we want to write really truly portable code using containers. So from the outset, let's say you're starting a new project. From the outset, make the image definition part of your code base and continually rebuild your Singularity image from it, and develop your code by running it in the Singularity environment. So whatever dependencies you need for your program, install them in the image, and really commit to only running your code in the Singularity image. It's very easy, just prefix everything with Singularity exec, essentially. And whenever you encounter a dependency that's unmet, install it into the image. So this is kind of annoying in that this forces you to build up your environment from scratch, but it's actually not that difficult, and in the end, your code will work everywhere. So I think it's well worth the effort. Just some comments on reproducible code in general. I would say this requires a couple of things. You just need to develop your code within the confines of a very widely available execution environment. Oftentimes, this can be a single programming language like Python or Node.js, but Singularity and Docker are like a stronger form of isolation. And the nice thing about containers is that they ensure that you don't accidentally violate those boundaries. And finally, you want to provide an automated way of sort of bootstrapping the environment on a new host. In Singularity, it's as simple as just running build or Singularity pull to get the image. Yeah, so if you are a researcher and you work in research computing, I would encourage you to develop your new projects inside containers and release the definition file with your project. Or even better yet, build the image yourself and just upload a pre-built image to the official Singularity library. It's free, and you can just make a note of the address of the image in your README and give that to users. These last few slides are not super important. They're just comparing Singularity to some other technology. We've looked at Docker before. Docker is mostly for the cloud. I think I did, in one way or another, mention all these things. So I'll move on. This is just a shameless plug for a tool I use for using Docker to develop things locally. So Docker is well worth looking into as well. And if you're interested in streamlining your workflow, then I have this repository available on my account. Kubernetes is something that's more or less orthogonal to Singularity. It's basically for managing containers, and reportedly you can actually have Singularity sitting inside of Kubernetes. And finally, Spec. Spec we've looked at before. Spec is a really nice tool. It also provides reproducibility similarly to Pippin, in that you can have a spec.yaml file which records all of your dependencies. It's also a really nice and powerful build tool. So Spec is nice. You can use it happily inside Singularity as well. So I would not say that Singularity supplants Spec in any way. All right, and thank you very much for listening. That's the end of my slides. If you like this tutorial, then please leave a star on GitHub. That's how I know you read it. Yeah, so I'm happy to answer any questions you might have. I might not be able to answer all of them. Again, I am by no means an expert in systems or containers. I work in natural language processing and machine learning. But yeah, I'm happy to open up to questions now.
Anybody that's got a question, please go ahead. I know that you all worked out many of the questions that were asked back behind the scenes. So the first question, I looked down, how does Singularity compare to Shifter? And I think you and I were chatting about that, and you hadn't used Shifter at this point.
Yeah, I actually haven't heard of Shifter.
Okay.
So I have a question. Okay, can I ask
Sure.
that?
Yeah, go ahead, David.
So you partially covered it, and that is, the partial part that you cover is, when you download an image from NVIDIA website and start building on top of that. But I have other images that I don't have the def files for, so I just have the binary, and it wasn't clear if I can build on top of that without changing the mount points, for example, or other stuff that's already being done by someone else, or should I bother that someone else to get me the def file?
So you should not require the definition file. In fact, when you are pulling from the official Docker, or sorry.
Well, I'm not pulling. I'm just, just have this file.
Oh, I see. Yeah, you should still be able to use it as the basis for a new image. You don't need the original definition file of the base image in general to build a new image on top of it. So I'm sure somewhere in the Singularity documentation you can find out how to use a local image file as the basis for a new image.
Okay, thank you.
Looks like we've got a question in the chat box. How well does Singularity work in an HPC environment with GUI applications and visualization software like ParaView? I guess that's probably a question dependent on how it would parse the GUI out to your remote resource.
Yeah, that's a good question. I have not used it extensively with GUIs, but I did go through that example that pops up a matplotlib window. I didn't show it for real because I just didn't want to risk doing a live demo, but yeah, I've gotten it to work over SSH. It's really nice because at Notre Dame, their Python installation by default does not include TK, so you actually cannot use matplotlib on their head nodes. And Singularity made it really easy to install my own version of Python that did have TK support, so that was really nice. As for something more elaborate than matplotlib, I don't know, but it did work for that use case. I can attest to that.
Okay. Other questions?
Actually, I have a question, if possible.
Sure.
So, in my experience, running MPI jobs with Singularity is essentially very tricky because you need to build a Singularity image that has an MPI version that is compatible with that of your host, which de facto defeats the whole purpose of Singularity because you end up having to run one image per HPC cluster. Is there a workaround that, a way around that, or?
So I don't use OpenMPI, but that definitely sounds like a really annoying issue.
It's not even specific to OpenMPI. I mean, you need an MPI that is compatible with that of your host, whether it's OpenMPI, MVPH, Intel MPI, or whatever.
I can chime in here since we have had that discussion extensively at Anchor. So the most recent version of MPI are using, for different vendors, besides one, which I don't remember which it is, are using a compatible API that they can be interchanged. However, if you run that on the Ethernet or on some Ethernet layer, Singularity will abstract that away. But if you want to run on the InfiniBand or any other more sophisticated things, you need the drivers to be the same into the image and into the machine, so you get back to that annoying part that you are discussing.
Got it.
Okay, great, thanks.
Other questions? Brian, I think that does it. I really appreciate you doing this. This has given me a renewed interest in carving out an hour or two of time to work on this some more. It's we're starting to develop workflows using Singularity, and I need to really crack down and separate the wheat from the chaff. I want to make sure moving forward I do all of this properly. But I picked out a whole lot in your presentation that's certainly going to apply to what I'm working on.
Yeah, thank you so much. This was really fun.
You had a great turnout. I think we had 72 people there for quite a while. So despite the
awesome.
Summer session, yeah, you had a great group. And we'll definitely, Brian's slides and his presentation, the recording will be available at the usual places. Brian, I'll copy you on that too, so everybody's got knows where to look for things.
Oh yeah, sure. I'll put my slides on GitHub too.
Okay, that'll be great. I really appreciate it, everybody, and we'll cook something up for next month.
All right, very cool.
Thanks a lot.